My name is Florian Wenzel. I'm a PhD student at TU Kaiserslautern and Humboldt University in Berlin. And thanks for the organizers for organizing this amazing workshop and giving me the opportunity to present my work today. This is joint work with Theo Khalifa-Schuh, Christian Donner, Marius Kloft, and Manfred Obber. And I'm going to talk about scalable log-shed Gaussian process classification. So GPs are quite cool building block for building probabilistic models, for example, a classification model, because they give you non-parametric priors and they give you a nice notion of uncertainty. So let's directly jump into the model. We have our training data x and y, and the model consists of placing a GP prior and a latent decision function f, and then squashing this function through a squashing function sigma over here to get probabilities for your labels. And in this work we use the logistic link function. But you could also use different link functions. The aim in, based on machine learning is always to compute the posterior of our latent variables, and then we can use that, for example, for performing predictions. But it's not that easy, and since we are in the approximate inference workshop, we want to approximate this intractable posterior, and the way we're going to do it is to use variation inference. And yeah, I guess you all know it, but just a quick recap, variation inference means that you define a class of easy distributions or easier distributions, and then you want to find the closest fit from this class to your posterior, by typically minimizing the equivalent divergence. So the aim in our work is that we want to develop a faster GP classification algorithm than former approaches. And the way we want to do it is to use efficient closed-form updates, and we want to get rid of any sampling or quadrature methods. And we want to have a scalable algorithm so that we can apply it to data sets of millions of data points. All right, let's speak about the first goal, how to get efficient updates. So the problem is, for an efficient variation inference algorithm, is that we have a non-conjugate problem. So if we try to apply variation inference directly, we typically have to rely on sampling. And our idea, we want to find a way to get around that by applying a technique which is called data augmentation. So we want to augment our model by new latent variables in order to get better properties. So here we have our problematic logistic link functions, and we make use of this integral identity here. So you actually can express the logistic function as an expectation over a squared exponential function with respect to some distribution P of omega I. So, but what is this P of omega? Turns out that it is an instance of the so-called Poier-Gamma distribution class, which was introduced by Paulson and Scott in 2013. So I don't want to go into much details here, but you can, for example, define the Poier-Gamma distributions by their moment-generating functions, and this will be actually a sufficient characterization for our inference algorithm later. So let's try it and augment our model with Poier-Gamma variables. Then the joint distribution looks like this. And now the likelihood function looks much easier than before. So we have just actually an x-squared exponential function here, which is proportional to a multivariate Gaussian distribution. So if you look at the full conditional distribution of f, that means the distribution of f conditioned on all the other variables, you see that this is actually just a GP regression posterior. And this can be computed in closed form. And this is much easier than a GP classification problem. And this will serve as basis for deriving an efficient inference algorithm later on. But before that, let's quickly talk about the second goal. So we want to have a scalable algorithm. The problem with Gaussian processes is that inference typically scales cubically in the number of data points. And to get around that, we apply the well-known concept of sparse Gaussian processes. So the idea here is to introduce a set of M inducing points and then connect the original GP with them, and they act like pseudo-observations. And later we will marginalize out F and just having U in our model. And this can be viewed as a low-rank or sparse approximation to our original GP. And it turns out that the complexity can be actually reduced to be cubic in the number of inducing points, and it's now completely independent of the number of data points. Alright, so just a quick recap. This is our final augmented model. So we have the labels Y, we have augmented Fourier gamma variables omega, we have the original latent GP F and inducing points U. So now we can talk about inference. So we want to apply variation inference to the marginal joint. So F is marginalized out here in order to get this sparse representation of the GP. And we follow a structured mean field approach and impose Gaussian distribution on the sparse GP with three parameters, mu and sigma, and then Fourier gamma distribution on the Fourier gamma variables. And now it turns out that we can compute the variational lower bound you typically get in variation inference in closed form, and it actually can also be expressed as a sum over data points. So you can now apply stochastic optimization in order to optimize it. So we have the variational objective in closed form, and this is different to approaches before, because there we always had to use sampling or some numerical integration methods, at least for parts of the objective, in order to compute it. Now we have the complete objective in closed form, and we can analytically compute the natural gradients. And this gives us an efficient second-order optimization scheme. So let's see how it performs in practice. So we perform some experiments and compare our method, XGPC, which is implemented in Julia, against the state-of-the-art in terms of fast Gaussian process classification, which is scalable variational Gaussian process classification by James Hansman et al. And we use their implementation in GPFlow, which is based on TensorFlow. So we compare both methods on a variety of different data sets, ranging from 1,000 points up to 11 million points. And so you see that both methods actually have like a similar prediction performance. So our method is a bit better on 3 data sets, and Hansman, the SVGPC method, is a bit better on the Higgs data set. So, but if you look at the runtime, we see a big difference. So we plotted the runtime in logarithmic scale on the y-axis, and here you can see that our method is actually faster up to 1 to 2 orders of magnitude on all data sets. So we can look a bit more deeper into the optimization. So we plotted here 2 performance measures as function of time. Left you see the log likelihood, or predictive log likelihood, and right you see the prediction error. And for both performance measures, you see that our method is actually quite efficient and reaches the local optimum after a few iterations, where SVGPC takes much longer. So we see this behavior in actually all the data sets we compared. So I want to highlight here again that this speed up is due to having more efficient second order updates. So because in SVGPC you had to use standard gradients, and we can use natural gradients now, and this is much more efficient. So let me conclude here. We propose a fast Gaussian process classification model, which is built on Fourier gamma data augmentation and inducing points. We achieve speed ups of 1 to 2 orders of magnitude by being still competitive in terms of prediction performance. And we have a method which scales to millions of data points. Yeah, and in future work we want to extend this framework to multi-class GP classification. Thank you for your attention.
We have time for one or two questions. Any questions?
Hi. So one of the issues that often occurs with Gaussian process models when you try to run them at large scale is not only the cubic complexity of the inversion of the covariance, but also the numerical stability of that inversion. Especially if you're working in floating point, it's often just not possible to invert the matrix because your numerical routine fails. I'm wondering if you have any similar sort of situations that occur here and whether your method somehow addresses those problems. And yeah, thank you.
Yeah, I mean, for us, it was actually not that problematic. So, I mean, we do this standard trick of adding just a bit of diagonal noise or like a diagonal matrix to the kernel matrix. But, I mean, if you have thoughts about that, if it's like, and it can be problematic, I could be curious.
Yeah, thanks for a really lovely talk. Really nice work. Could you say a little bit about what you did about the hyperparameters of the GPs in these experiments?
Yes. So, yeah, I go back to the original lower bound here. So, I mean, we do the standard stuff in like an empirical Bayes approach. So the evidence is actually conditioned on your hyperparameters, and so if you want to optimize the hyperparameters, you can alternate between optimization steps with respect to your variational parameters and the hyperparameters. And for that, so we have like an outer loop of optimizing the hyperparameters, and here we use Atom to optimize the hyperparameters. So, but in the plots I showed you, we actually fixed the hyperparameters to just compare the inner loop of SVGPC in our method, because the outer loop is quite similar. But there's ongoing research, so now we also have like the outer loop of optimizing hyperparameters, and it also works out. Okay, thanks.
I'm wondering about the B-field factorization that you use in your variational posterior, and whether you have compared the actual uncertainty that you get in your GP estimates to, say, a MCMC algorithm that's been run for many iterations.
Yeah, that's a good question. So we actually want to do that, but yeah, we haven't done it so far. I mean, one promising thing is that, like here, when you see on the left side the predictive log likelihood as performance measure, we saw in a couple of data sets that our method actually compares a bit better than SVGPC. And like the log likelihood probably gives you, if the predictive log likelihood is better, then it is kind of indicates that your uncertainties are a bit better calibrated probably. So we hope that our model probably represents uncertainty a bit better than the approach before, but we haven't compared it to like an asymptotically exact method like Hamiltonian Monte Carlo. But would be interesting, so yeah, I'm gonna do that.
Let's send to the speaker again.